Hey everyone, welcome to another video. Now, we are moving on to the newer content from Surds in year 10. Now, a lot of the operations with Surds we covered in the previous series, the year 9 series on indices and Surds. So we're just jumping straight in now to the new things here and the new kind of patterns and operations that we've been doing with other algebraic terms and numbers previously, and applying this to Surds and seeing if it works in the same way. So this video then is going to be about expanding brackets when Surds are involved, and we're going to see if this works the same way. Now, I have a simpler question here to start off with, just because I want to start thinking about those same patterns and doing this a long way and trying to uncover the relationship between this outside number, the number outside the brackets, and the ones inside the brackets. So, a little thing to remember is anytime we have a number outside of brackets, a multiplication is assumed here. So, in other words, what this thing is telling us is we have 4 lots of 3 root 5 plus root 6. Okay, now when we say 4 lots of something, remember multiplication is just a shorthand for taking this number and adding it 4 times. So let's just go ahead and do that and see what happens. So this thing up here, 4 outside of 3 root 5 plus root 6, or 4 lots of 3 root 5 plus root 6, is the same as going 3 root 5 plus root 6 plus 3 root 5 plus root 6 plus 3 root 5 plus root 6 plus 3 root 5 plus root 6. Okay, perfect. That took way longer than I was hoping, but now we can just identify the like surds. So I have 3 root 5 here. Well, I have the like surd here is the root 5. So that's what we're considering when we want our like surds. And all of these give me a like surds too. So root 6, root 6, root 6, and root 6. So all of the operations here between these numbers are addition. So that means we are going to be adding all of these numbers together, all of these like surds together. So here I've got 3 root 5 plus 3 root 5 plus 3 root 5 plus 3 root 5. We remember from last year's content that when we add like surds, it's similar to just doing algebra. So if we had 3x plus 3x plus 3x plus 3x, that would give me 12x. So that means if I replace this with root 5, so 3 root 5 plus 3 root 5 plus 3 root 5 plus 3 root 5, then my product here, this thing, is going to work in the same way as the algebraic term. So that would give me 12 root 5. Okay, so therefore, if I add my like surds with root 5 together, that's going to give me 12 root 5. And my root 6s all adding together, I have 1, 2, 3, 4 root 6s. So if I add those like surds, that's going to give me 4 root 6. And as we probably would have guessed, if you remember from previous years when we first looked at expanding brackets, what we always seem to get is the outside number, a result which is the same as the outside number multiplying by this first term and then multiplying by the next term. So let's just check if that happened. Well, 4 times 3 root 5, these outside numbers are going to multiply, giving me 12. And my 4 times root 6, well, my 4 is just going to multiply by the root 6. So a shortcut way of writing 4 times root 6, or one lot of root 6, is just going to be 4 next to the root 6. So surds as well follow the distributive law, which we learnt in previous video series. So what that means, the surds follow the distributive law. So if I have A outside of B plus C, I'm going to get a product of the outside number with both of the inside numbers. So it works for algebra, it works for surds as well. Now, surds work as well with following the distributive law when we consider binomial products. So something like, let's go with another example. If I have 4 plus root 3 times root 3 plus 2. Okay, so these two binomial expressions are getting multiplied, because anytime we write brackets next to each other, they're being multiplied. And we can look at this like we would any algebraic expansion. If you remember, we looked at this in terms of area. So anytime two things are getting multiplied, it is the same effect as, we can think of it geometrically as an area. So, because with an area, we are multiplying one dimension by another. So we can have this 4 plus root 3 as one dimension. So we have 4 with an additional root 3 being added. So this total length is going to be 4 plus root, plus root 3. And this guy here is going to be root 3, and let's make this distance 2, so that we get a total length here of root 3 plus 2. Okay, so if we treated this as an area, to find the total area, we just want to find all the separate 4 areas and add them together at the end. So this top left-hand corner gives me 4 times root 3, which is just going to be 4 root 3. This top right-hand side is going to be 4 times 2, which gives me 8. This bottom one is root 3 times root 3. Now remember, if you multiply two surds that are the same, that's just going to be the actual number. So anytime I multiply, say, the square root of 3 by the square root of 3, that'll give me 3. Or the square root of 5 by the square root of 5, that will give me 5. And this last one is going to be 2 root 3. Okay, so now we want to add all of these together. So I have 4 root 3 plus 8 plus 3 plus 2 root 3. And I can group a couple of these terms. I have these just like whole numbers here. Well, sorry, not like whole numbers. These are just whole numbers that I can regularly add. And I have like surds as well. So 4 root 3 plus 2 root 3 gives me 6 root 3. And 8 plus 3 gives me positive 11 here. So we could have gotten the same thing if we just did our FOIL method. So if we multiplied the 4 by these terms and the root 3 by these terms, we would get the same thing. 4 times root 3 gives me 4 root 3 down here. 4 times 2 gives me 8, which I get as my next term. Root 3 times root 3 just gives me 3, my next term down the bottom. and root 3 times 2 gives me my final term. So surds work in the same way as binomial products. So surd expansion is the same for binomial products. So just a revision to what we did with algebra when we did these algebraically. So a plus b times, let's do c plus d, that we ended up getting the first multiplying, the outside multiplying, the inside multiplying, and the last multiplying, or FOIL, first, outside, inside, last. So surds work in the exact same way. And we're going to explore in the last two examples just some of the other patterns we saw for expanding brackets. The first one we're going to look at is a perfect square. So 3 root 2 plus 5 root 3, all squared. Now, if we have anything squared, that just means the expression multiplied by itself. So that would give us 3 root 2 plus 5 root 3 times 3 root 2 plus 5 root 3. Okay, and we're just going to use our FOIL method. So we're going to multiply this here, these here, and these here. So 3 root 2 times 3 root 2. Let's actually just do this the long way. So this gives us 3 root 2 times 3 root 2 plus 3 root 2 times 5 root 3 plus 5 root 3 times 3 root 2. And finally, we're adding 5 root 3 times 5 root 3. Okay. Now, this first term, my outside numbers are going to multiply. So 3 is going to get multiplied by 3. That gives me 9. And then root 2 times root 2 gives me 2. So that's going to be 9 times 2. That gives me 18. My next one, 3 root 2 times 5 root 3. The outside numbers are going to multiply. That gives me 15. And root 2 times root 3 is going to give me root 6. And on the next one, I get 15 outside of root 6 again. And to that, I'm adding 5 root 3 times 5 root 3. So 5 times 5 gives me 25. 25 times root 3 times root 3 gives me 3. So 25 times 3 gives me 75. And notice that in the same way with perfect squares, we just have here 2 lots of the middle terms. So it works in the same way as perfect squares. So when we had, a squared plus 2ab plus b squared. This kind of pattern that we observed here in previous cases with algebra still is the same for surds. So now we just need to add the numbers. Adding 18 and 75 gives me 93. And 15 root 6 plus 15 root 6 gives me 30 root 6 here. Okay, let's look at one more case here, and that is the case of perfect squares. This is the final pattern for binomial products that we looked at with algebra. So if we had, for example, 2 plus root 5 and then 2 minus root 5. And this final one is going to be quite important as we begin to look at further surds topics particularly in the next few videos. But I'm just going to expand these using the FOIL method again. All of these terms are going to interact. So 2 times 2 gives me 4. 2 times negative root 5 gives me negative 2 root 5. 2 times root 5 gives me positive 2 root 5. And root 5 times negative root 5 gives me negative 5 here. Because root 5 times root 5 gives us a rational number, gives us just a 5. Okay, now paying attention to these two middle terms. With our difference of 2 squares, remember when we had the same terms here in my brackets, but just a different sign separating them, I always got the first term squared minus the last term squared, because the middle terms end up cancelling each other out. Because negative 2 root 5, if I were to add 2 root 5 to that, I would just get 0. So as a result, I get 4 minus 5. Or, if I want to look at this with my difference of 2 squares, this is the same as my 2 all squared minus my last term root 5 all squared. And when I do this subtraction, I finally wind up with negative 1. So all the things that happened with our algebraic terms when we looked at regular distributive law expansion, as well as expanding binomial products, as well as perfect squares, as well as difference of 2 squares, they work the same way for surds.